Example, integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. We will do, you can try to do your substitution, give up at some point, and then realize that polynomial over polynomial maybe should be done using partial fraction decomposition. Make sure you have enough space for this line. This will be a long line. We're first going to perform some factoring for the denominator. Numerator does not matter. Denominator can be factored as x plus 2, and 2x plus 1, and I will not be reviewing this right now. Basically, you factor out x, and then you have quadratic function. Quadratic function has roots. You find those roots, factor out. You can check pre-calculus class or algebra class. I have videos on this, to how to factor quadratic functions. And now check this out. We're only looking at the denominator over here. And we're going to use this to create 3 integrals, 3 tiny integrals. We're going to go back to the table. In your case, it was the green table, or any table is fine. And this is what you should write down there below each case. When you have ax plus b, that is linear r in the denominator. You see, linear piece in the denominator. This can be written as a over ax plus b. Which I'm going to do right away, I guess, to make a better link to this information. So I see x, and this is exactly what I'm talking about, linear. Linear will be written as a over x. And that is the first integral. So we're breaking this big integral into smaller integrals. X, since it was part of the factoring process, gives my first integral. Plus this piece, second piece, x plus 2, is also linear. So it also can be written as a over x plus 2. But since we used a, let's use b. b over x plus 2 dx. That's the second integral. Plus, and the last piece is also linear. Linear means not quadratic, not cubic, not square roots. So that's going to be c over 2x minus 1. Good job. C over 2x minus 1. And it's the third integral. Partial fraction decomposition decomposes a fraction into partial fractions. So now I have 3 smaller integrals. Before we move on with the integrals, I wanted to point out we are lucky to have linear parts. If it's not the case, we might have what? We might have a case of linear being raised to a power. So I usually explain it as linear to k. Then how do? You still do a over x plus b, but then you have to do one more a over x plus b squared, and then cube, and the fourth power, until you hit that k. If it's k to the 5, then you have to accumulate them all. That's why it has a, b, c, or some people use a1, a2, a3, a4. Then you don't have to use all the alphabet, because English alphabet is pretty short, actually. How many letters do you guys have? 26. We have 33. So that is cooler. Anyway, then what if you have not linear? What if you have quadratic? Ax plus bx plus c, quadratic. Then the formula changes. Instead of a over that thing, you'll have to have linear at the top, so it's 1 power less all the time. When it was linear at the bottom, the top was a constant. Now there's a quadratic at the bottom, so the linear will be at the numerator, ax plus b. Finally, the combination, if it's linear to the k, no, if it's quadratic to the power, you have the same logic, ax plus b, x plus b, x plus b, with all different a's and b's, over no power, first, second power, so first power, second power, third power, until you reach the power you need. Those are the scenarios, and I have really good videos for each scenario I made for each example from your homework. So kind of you have lots of homework being solved. I will post it later. Let's continue. The whole point is now we're ditching integration and actually just working with fractions. We need to find is a, b, and c. So the goal, I was just talking in my other class, WTF, want to find, I really find it's bad, like don't do that. But it was a lecture I saw, and all the notes have WTF, 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 WTF. So I thought maybe it was a mood of the class, you know. But no, the teacher meant want to find. We want, that's not age. Want to find, let's write it down, A, B, and C, basically those coefficients. In this case, we have only 3. Sometimes you'll have 5, 12. This is where computer comes in. Computer actually knows partial fraction decomposition, does it faster. Okay, step 1. You multiply by the denominator at both sides. So I will write it down before multiplying. This is usually skipped step, but it will be easier to explain. Let's write down just fractions, because there's a property of integration that integral on the left-hand side equals to the integral on the right-hand side. We had it in Calculus 1. There's a proof of this theorem. So the left-hand side big fraction equals a over x plus b over x plus 2 plus c over 2x minus 1. So we're ditching integration, and we're going to be working to find a, b, and c. Why? Before we keep doing it, I can actually ask you, what is the integral of a over x? It's natural log. So that's simple. What is the integral of b over x plus 2? That's a natural log. What is the integral of c over 2x plus minus 1? Natural log divided by 2, right? Divided by the leading coefficient. So that's the whole idea. This is scary and huge and uncomfortable, equals to 3 very nice, comfortable integrals. So that's why partial fraction decomposition is actually a pretty popular technique. We just need to find a, b, and c, and the answer will be simple after that. To find a, b, and c, don't yawn, that's contagious, you know. No. We multiply by denominator everywhere. 2x, x plus 2 to x minus 1. Left-hand side and right-hand side. This is European notation, the tilted bar, and then you multiply. Do your own notation, whatever you like. But I like this one because it has good notes in the future. So I'm multiplying both left-hand side and right-hand side by the denominator to get rid of the denominator. Usually people don't write it down, all of this. They do it just in their mind. But for the good notes, I will show you why we're doing this. When you multiply left-hand side by the denominator, you just end up to have with the numerator equals. Then you have a times. And then take red pen and see what's going to cancel out. Since it was over x, x cancels out. Good note to mention, bless you. In Europe, we're writing x in a cursive way, like so. This is x. So I was asking American students if they like it or not. They say they don't like it. So I had to train myself for 2 years to switch to this x. And you know what I told them? How do you cross this x? Like this? Right? So that's exactly what I did here. Think about that. If I don't use colors, it's like this. That's just so not practical. And that's why I like cursive more, but it's fine. Everything for my students, it's fine. So what's left? X plus 2, 2x minus 1 left with b. With a. What is left with b? X plus 2 canceled out with x plus 2. Then x left, and then 2x minus 1 left. What is left with c? The last one cancels out. And that's not a coincidence. This is how we making partial fractions. That's why they keep canceling out. 2x minus 1 cancels out. We have x, and then x plus 2. This is the equation we have. And we're gonna need to find, we don't need to solve for x. We need to find a, b, and c. And I will introduce 2 methods for you to do that. Method 1, I call it way 1, because it's faster to write. You plug some convenient numbers. I'll call them good, but I mean convenient. Convenient values. Just plug something into x, whatever feels good to you. Just for example, let's write down. For example, anything convenient works good. What's the first convenient number comes to your mind? 0. 1 also works. So 0, 1, minus 1, 2, minus 2. Again, I could plug pi. I could plug what? 17 over 3.5. But like, why would I do that? You know, it's still gonna work. It will give me exactly the same solution, but it will take so much extra work. That is why it's called good or convenient. be smart, basically, when you try to optimize your work. So if I plug 0, left-hand side becomes what? -1. Right-hand side becomes, check this out, how you do it fast. Either you actually FOIL this stuff, which means distribute, right? Most people don't do that. They just do it fast. X is 0 plus 2, that's 2. X minus 1, 2 times minus 1 is -2. So does it make sense? -2a. Let me know if that's not correct. Plus 0 plus 0. Smiley emoji. From this, you can right away solve for a. A is what? 1/2. Put it in the box. This time it will be pretty cool if you put solutions in the box, because it will be so much writing. You'll have to find those things later, and then it will be too much to scroll. So boxes really help in this case. And on the quiz, you should put your solutions, final answers, in the box or circle. Yes?
Where do you get the -1 from?
-1 from left-hand side, when you plug 0 everywhere. 0, 0, 0, 0, and so on. Okay, we found A. For others, what do you want to plug now? -2, why? That will cancel out, and that will cancel out. So just convenient. Again, you could plug anything, but this is convenient. If you plug -2, you will have 4 or -4. So -2 squared. So I'm plugging x everywhere, left-hand side and right-hand side. Maybe I should write down once. Let's do it once. -2 squared plus 2 times -2 minus 1. This is where I got 0 last time. I plug 0 plus 0 minus 1. Left-hand side is this. A times 0 or not? A is times 0 because -2 plus 2 is 0. How about B? B is not times 0. B is multiplied by -2 times what? -4 and -1 is -5. C, 0. So again, I'm plugging -2. Here, for the first term, it gives you 0. For the second term, it's not 0. For the third term, it's 0. And that's why we chose it. We chose it for that specific reason. Because we notice it will make lots of stuff 0, and it feels good. Now we can solve for B. Simplify left-hand side, right-hand side. -4 plus 4 is 0. So -1 minus 1 equals 10b. B, and put it in the box, is -1/10. Put it in the box. Finally, we need to find C. What other number do you want to plug? 1/2. 1/2 will make the first term 0 and the second term 0, but then you'll have to struggle with fractions. Still works, it's fine. You could plug 1 and just have numbers on the left, numbers on the right, plug A and B, and you're good to go. But 1/2 is also a good choice, so whatever you say. Or x equals 1, or x equals -1, whatever. So that is the whole point, that it's a good method because it's pretty creative. 1/2. Now I have to calculate stuff on the left. 1/2 squared, blah, 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 fractions. And I do have it here. So it's actually, again, 0 plus 0 minus 1, which is convenient. Oh, no, it's not. Is it? Oh, yes, it is 1/4. Oh, but it's 1/4 plus 1 minus 1. Yes, so it's 1/4. Equals 0, 0, C. And then I have 1/2 times what? Plus 2, but what is it? 1/2 plus 2? 5/2, like so. 5/2. Calculate. 1/4 equals C times 5/4. Multiply by 4 times over 5, and C becomes, 4 cancel out with 4, 1/5, I think. So this is going to be lots of algebra, and you all are really good at algebra, right? And you never make any typos because we're such a perfect human beings. When you zoom out, that was irony if you did not get it. That was ironical. Anyway, We all make lots of mistakes in algebra, so you have to be careful here. People with good handwriting will win in this situation because they will have everything scheduled. Just a second. The goal is to plug these things into those small integrals. We're going back into integrals now. What is your question?
Did we not like plug in A or B? I'm just confused there completely now.
You could. So the question is, should we not plug A and B over here? Yes. Then you also can solve for C. That's why there are several methods of doing it.
Okay, so what did we do here?
We plugged 1/2 everywhere. Left-hand side gave me a number, 1/4. Right-hand side gave me this 0 and this 0. Because 2 times 1/2 is 1, 1 minus 1 is 0. Make sense? So I only needed...
Okay, all that times 0.
And it's like not coincidence. People chose it from the audience because they noticed it. They noticed the root of 2x minus 1 is 1/2. So if you plug the root, it will make 2 zeros, and that's why it's a nice choice. But actually, you could plug any other number. 1 minus 1 pi. It's still gonna work. It's just lots of extra calculations. Yes?
So we use the 5/2.
5/2 by plugging it here. 1/2 plus 2. Common denominator is 2. 4 plus 1 is 5. Common denominator, 1/2 plus 4 halves. 5 halves. And it came here. Make sense? Good questions. Now we're going back to integrals. So plug into small integrals. We will have equal sign. The first integral was, let me zoom. See, when I'm zooming out, I see my squares. Even if I zoom out a lot, I see where my ABC is. And that's why it's a good idea to put them in circles or squares. A over x. A is 1/2. I would do 1/2, 1 over x, because it looks better. Maybe I'll put it in green for you. So 1/2, and it was 1 over x. Plus b over x plus 2. Let me zoom in. B is minus tens. Put it in parentheses. 1 over x plus 2 dx. Finally, c. And again, I'll put it in green. 1/10. This is my b. We found it. Interesting. Delete. Finally, the last one is... Some stuff happened. Who knows what it is? Okay. C is 1/5, and then what was it? 1 over 2x minus 1 dx. So now I have 3 integrals, and we're ready to finish them. And this is the favorite part of students because this goes fast. You tell me, 1/2 1 over x gives you what? ln x, correct? Absolute value, someone mentioned, good job. Minus 1/10, then what? Natural log of x, no, x plus 2, correct? Absolute value divided by the leading coefficient, but in this case it's 1, so it's fine. Not the last one, plus 1/5, what? Natural log over 2, exactly. So people who don't know why we're doing this, this is a U sub, shortcuts. But, shortcuts. But you have to actually do, if you don't know shortcuts, that's fine. Just perform your substitution, you'll be fine. Thank you. Plus C, amazing. So after all of this hard work, don't forget to put plus C. This is a big answer, and partial fraction decompositions. We decomposed the big integral into the smaller integrals, and it worked. We found ABCs, and then integration was piece of cake because we learned shortcuts. That's why I like shortcuts that's why I'm pushing them, even though I don't require to know them. But it's cool if you do. It makes it faster. What do you think about that? Way 2. Let me show you way 2 because this is a very international explanation of how to do partial fraction decomposition. Way 2. Way 1 was plug good values. Way 2 will be actually the official way of doing it, and that's what you will see in the book. Collect. terms. Collect terms. This is the official way, so I do want to explain it. Let's rewrite the original fraction because we need to see it in front of us, so it's just better this way. Bless you. Which was x, let's go fast, x squared plus 2x minus 1 equals a over x plus b over x plus 2 plus c over 2x minus 1. Let's assume we did not find a and b and c yet. No, that is not correct. This is not what we have. Yeah, I need the one with no fractions. That's the one. Sorry about that. Looked one line higher. A, x plus 2, 2x minus 1 plus b, x at 2x minus 1 plus cx, x plus 2. Put parentheses everywhere. It will save you from losing some negative signs, and in general, it's good. When you type it in, it will save you too. So collecting the terms, the idea is we're going to collect the coefficients that are standing in front of x squared right now. And that's going to be x squared. Check this out. I will only write down coefficients attached to x squared on the left-hand side. On the left-hand side is just this 1. So 1 equals. Then it's 2x, it's not x squared, minus 1, not x squared, skipping 1. So it's only coefficients in terms in front of x squared. On the right-hand side, you can take a pencil and quickly distribute. It will be a times, you guys call it FOIL, but actually distribution doesn't matter what the order is. 2x squared plus 4x minus 2 minus x. I just randomly did that, and it's correct. FOIL, you know, international students, we don't know what your FOIL is because you can randomly do it. You don't have to remember the order. I think it's actually more complicated. Anyway, so now what is standing in front of x squared? 2 or 2a? 2a, because you still need to distribute a. I just didn't do it. It's too much work. Then, what is, I will not distribute bx, 2x minus 1. What is standing in front of x squared there? 2b. You can do it in your head. Some people like, I don't want to do it in my head. But actually, you can. Some of you have lack of confidence in algebra. And I need to tell you that you can do that. Just do it. It is x, 2x squared minus 2, right? Times b. But again, minus x. It's too much work to distribute every time. What if you have 5 terms to distribute? You have to do it in your mind. bx times 2x. Yeah, that's 2b. Others are too low in their power to be considered. And the last one is c. That's it. The other one does not count because it has lower exponent. Like so. First equation is collected terms that are standing in front of the x squared. Let's continue. X to the 1. Left-hand side gives you what? 2. Because it's the only guy standing in front of the x. Right-hand side. 4a and minus a. Check this out. This guy has 4x and this guy has minus x, and both are multiplied by a. Yeah, I would, but I want to have good notes, so I will keep it like so. Or else people will ask. So then, what is standing in terms in front of x for with b? Minus b, amazing. And the last one? So 2 times c times x. That's 2c. Make sense? Are you keeping up? Like what's going on? Finally, x to the 0 is notation for constants. Constants. Let's collect constants on the left-hand side and right-hand side. Because x to the 0 is 1, so we do assume in many classes that this can be written as 0, as 1 times x to the 0. So left-hand side is visual, it's minus 1. Right-hand side, what do we have? Minus 2a. What else? 0b, exactly, skipping b, and then what? 0c, skipping z. There's no standing alone coefficients with b and c. So this is the system of three equations with three unknown a, b, c by the theorem of system of equations. This has a unique solution because it's enough to find three variables. And we teach you this, how to do it in pre-calculus class using, usually we teach you substitution method, not U substitution, just substitution method or elimination method. Elimination method. You also can use matrices if you know that, and coding if you know that. Your calculator can do it for you as well. So I have videos on this because I was teaching college algebra in this school. I will attach for you to review if you want. But substitution method is very intuitive. You solve for A and you plug everywhere else. Let's solve for A. A is what? 1/2, which is exactly what we had before. And then you plug everywhere you see A to reduce number of, not this, to reduce number of unknowns and number of equations. So the first equation becomes 1 equals 2 times 1/2. That's just 1 plus, well, maybe let's write down. 2 times 1/2 plus 2b plus c. The second equation becomes 2. 4a minus a is 3a. So 3 1/2 minus b plus 2c. Now you have system of two equations with two unknowns. It's enough to solve, blah, blah, blah. And you get exactly, using any method you like. Elimination method here will be actually pretty neat. And you get exactly the same solution, which is, what was it? 1/10 for b. Here it is. B is minus 1/10, and C is 1/5, I think. 1/5, and then you go and integrate just like we did before. Two different methods. This is official method. It's actually part of the theorem and the proof. Collected in terms with corresponding x's, x to corresponding powers. And then you build a system of equations, and we teach you for so many years from high school and middle school, whatever, how to solve equations. Yes?
How do you get the 3 to the first 3 times 1/2?
So I'm plugging everywhere I see A. I plug 1/2. The first one was kind of visual, but the second one was 4a minus a. So I wrote it as 3a. So then I plugged 1/2 here into a and here. Make sense? So 4a in the second equation. 4a minus a is 3a, and then we know a is 1/2, so I plugged 3 times 1/2. Usually students like first method, but sometimes, surprisingly, second method is faster. Yes?
In the first method, how did you get like 0, -2, and 1/2?
0.
Like in the, if you scroll up.
Oh, the first method.
Yeah, like that.
You guess. That's what it says. Plug good values and just guess which one you want. That's a very classical question. Thank you. You look at this massive equation and you think, okay, by the theorem, whatever is on the left-hand side equals whatever is on the right-hand side. So I can plug any value for x as many times as I want, and until it's enough information to solve for a, b, and c. So I plug 0 because everyone likes 0. Then you plug 1, maybe 1, -1, maybe 2, -2. That's a classical choice. 10, you can plug 10. That's also easy to calculate. But people notice if you plug -2, it makes zeros. And then people notice if you plug 1/2, it makes zeros. So either you plug 0 or whatever makes zeros. Or just anything else, doesn't matter. So that's why it's kind of your choice. It's more creative this way. Second way is structured well. It's exactly one way of doing it. The first way is creative. So grading becomes interesting because people have interesting imagination sometimes. Good questions, people. More? Yes? What did you say? Yeah. Oh, that one?
Using the formula.
This one?
Yeah. Why are we adding?
Yes. A, B, and C will be explained in the next example better. So let me tell you, thank you. You're making a very good link with the next example. That's actually the most important of this chapter. It's not to teach you how to do algebra, but how to teach you to use the method. And I'll just show you the beginning of the next example, which is this. We have 3x plus 9x squared plus 17 over x squared times x minus 1. times x squared plus 9. Let's do that. And then I will just start it and then show you, and then we have the quiz. So, the table says, now it's in the factored form, which is very convenient. Sometimes in your homework you'll have to factor it by yourself, but when I became a coordinator of this class, I was pushing that on the exam. We should not torture students with factoring. Okay, we're not grading your knowledge on factoring. So now we give you factor denominators, which is very nice. So, on the test, the table says, check the table. The table says, if you see linear or linear to the power, you will use this form, a over ax plus b, or a over x plus b, a over plus squared, cubed, and so on. Let's see what we have. We have first x squared. X squared can be treated as quadratic or linear squared. And in this book, they actually want to treat it like so. They want to treat it as linear to the power 2. But actually, both work fine. You can treat it as an x squared if you want, and it works fine. So the first integral becomes integral a over x dx plus integral b. It will not fit, by the way, so maybe switch to another line. I just remembered now. A over x dx plus b over x squared dx. The formula of partial fraction decomposition says if you see linear to the power, you will have constant over that part, constant over higher power part, and until you hit that power. That is just the first piece in blue. How about x minus 1? We just did x minus 1. It's still linear. So we will have c over x minus 1 dx. You can also have a1, a2, a3, and so on. Or you can use the alphabet. And the last one is new. We did not do it before. That's called quadratic. This is quadratic. And quadratic has the shape like so. You will put it in the denominator x squared plus 9. And the numerator have to be linear because it's 1 degree less, which is ax plus b. But since we used a and b, let's use more letters, which is what? Dx plus e, f, you choose x. Doesn't matter, don't choose x. Okay. O, I saw O, but it looks weird. Any other letter is fine. Dx integral. So this is what we will be testing quite hard to see if you understand how to build those integrals. A over x, b over x squared comes from the x to the squared. C over x minus 1 comes from the linear part in green, x minus 1. And finally, x squared plus 9 is quadratic, so it's dx plus e. Yes?
Can't we write ax plus b upon x squared?
Yeah, you can do that. It works the same way, actually. If you create common denominator, you will see that. Some people do it. But I want to follow the book, so it's fine. This is important, so multiple choice questions will just give you this to see if you can understand how to break integrals on the exam. And in the homework, they also have multiple choice, which is good. One thing I wanted to ask you is, do you understand how to, so we need to find A, B, C, D, and E using all those methods we just mentioned. But when we do you know what integral it will give us? What is A over x again? Yeah, louder, you know what to do. A ln x. What is b over x squared? Who knows? Minus b x to the minus 1. Because it's x to the minus 2, then it's power rule. So we know that. How about c over x minus 1? What is that? C, let me put here. C, natural log of x minus 1 divided by 1. Exactly, good job. And the last one, you had it in your homework, 5.5, U substitution. Break it into two integrals, which will be dx over x squared plus 9 plus integral e, bless you, x squared plus 9 dx. Then the first one is done using U substitution. The first one is U sub, figure out. But the second one, let me put it in red. Do you know the answer for the second one? Arc 10, exactly. Someone actually knows. That's very impressive. This is arctan of something, and you have to figure out the constant. Arctangent of stuff. This plus 9 messes it up, so you have to factor it out, figure out the constant. But 1 over x squared plus 1 is arctangent, integral, that is arctangent. So breaking a big, ugly integral full of polynomials into smaller, cuter integrals. Most of them are easy, and then sometimes you use substitution or formula, we know. Usually we don't even do integration by parts. That's how smaller those integrals become. Just a second.